I'm pretty much going to pick up where I left off. There's been a lot of crust today, so this is going to be biased toward the deeper stuff. All right, this is, it's certainly one of the most iconic images of the Yulgarn. So this, these isotopes map showing a more ancient west and a younger east. And I guess in an effort to explain that east-west transition in terms of a geodynamic model, we had early hypotheses of, terrain accretion or arc accretion of exotic terrains. But then you've got the komatiite eruption, so you require very high temperatures. That granite bloom that someone mentioned, and it's spatial ubiquity. So that kind of pointing toward a plume. And I've just grabbed, so not favoring authors or anything like that, but some people were kind enough to provide cartoons. So in this particular paper back from 2012, so we've got a you and me craton, and they've actually inferred an eastern goldfields craton as well. So the plume impinges on the base of the lithosphere. The plume tail then is funneled into some kind of pre-existing weak zone. We get all those komatiites, and then for the cooler plume head, given the granites and so on. And then Rose showed this earlier on. It's a progression through those models as more data is added. This one was from David Moe, superimposed the komatiite hosted nickel deposits and this correspondence with these isotopic margins. And Graham has been a long-term proponent of this. And David Moe, they provided a cartoon as well. So again, showing something similar, this plume head impinging on the Yulgarn protocraton being channeled to the east. So we had these east-west models, and then enter Hugh, and I'm looking at the one that's ahead. Catch up. All right, yeah, okay. So same, and this is an older PowerPoint presentation. I'm on a different version. So a similar model. So we've got this Yulgarn protocraton in the west, so thicker depleted mantle keel. And the same thing here. So impingement of a plume, but maybe with a back arc setting for the eastern goldfields. So plus or minus a subduction zone into the mix as well. All right, enter Hugh now. And Hugh points out from the geochemistry data that it seems that we've got this more ancient east-west or east-northeast architecture, so running underneath the whole thing, with implications for models of evolution of the Yulgarn. And then why use crustal models from earlier on. So we have Moho depth on the left and Moho amplitude on the right. And again, we do see a similar trend, especially in the southwest Yulgarn. But arguably then you also have the northwest stuff with the thicker crust in the eastern goldfields. So bits of both, really. So then going to the deeper stuff, so the surface wave models, again, you've seen this, so 75 and 150 with the cross sections shown on the right-hand side. So again, I'm going to point out these things on the color bars. So taking an average over all continental lithospheric matter, AK135, that's what you get. So you're at the red end of the color scale. Then we've got something similar, an average over cratonic structure, and at 75 kilometers, you're roughly at 4.7 kilometers per second. If you go deeper, it decreases somewhat. And then, so you're going to have Proterozoic wave speeds somewhere in between. So first of all, we see in the Western Yulgarn, so very elevated wave speeds, so again up to 4.8-ish. So what are seismic wave speeds? What are they sensitive to? So they're sensitive to bulk composition and temperature. So in terms of bulk composition, we could codify that in terms of the magnesium number. So the higher the magnesium number is, the faster the wave speeds will be, and also the cooler it is. So the more rigid it is, the faster and the more efficient the wave speed transmission will be. So taking that So the blue colors, it's almost a proxy for age and thickness of the lithosphere, bearing in mind that this is a Polaroid shot of the lithosphere, so we can't do the time slicing, so lots of this is all of it is inference. But we do see that transition from a thicker lithosphere in the west to a thinner lithosphere in the east. But it's the Kalgoorlie-Carnalpy rift. We only really see that in the uppermost mantle. So in the 75-kilometer depth slice, we've slightly reduced wave speeds aligned with the Kalgoorlie and the Carnalpy terrains. So I would say what that is, yet if I say anything nutty, it's all on me, that's some expression of metasomatized, so rift-related melt that's fossilized there in the upper lithospheric mantle. We've had huge amounts of melting there back whenever that was, 2.6, 2.7. Then we go deeper, and I think what we're seeing here, we're seeing something similar to what Hughes proposed, so a more ancient, so east-northeast type architecture, with the deepest kernel, so the relict protocraton mantle queue beneath the western UNME and into the southwest terrain, and then a slightly less thin limb, so this continuous structure going across the central eastern goldfields. I guess one question is, so for this bit that stretches across the eastern goldfields, was that originally as thick as what we have in the UNME terrain at present? And that was thinned by the rifting with melt products being locked into the upper lithospheric mantle, or maybe not. What else do we have? We also have this orangey blob along the bottom southeastern Yilgarn Craton margin. So I would say that those wave speeds are too slow to be purely Archean. I think they're more in the Proterozoic range. I think the lithospheric thicknesses are more in that range. So I think we're seeing modification there. But I also think we're seeing the guiding hand of the more ancient east-northeast stuff. And we also see, like I showed before, so that east-west, that inferred fossil fabric in the lithospheric mantle in the shear wave splitting. Now we do see, for example, in the southwest terrain, maybe a wrapping around, so that might be more Proterozoic in age. But by and large, there is a pretty pervasive signal east-west right across the craton. And finally, what Rose showed, and I've come to love this stuff, the geochemistry, the time slice mapping. I found it really useful to interpret these maps. So we look at the youngest slice here. So we see that older West Yilgarn, where we've got the blue seismically fast wave speeds by inference, old, thick. And then we've got what I would say is the seismic expression of that rifting locked into the upper lithospheric mantle. But then we go deeper in the seismic model, and I think although the points are sparse, I think it replicates what we're seeing in these older time slices. So those older mantle extraction ages across the UNME and into the eastern goldfields, with the younger mantle extraction ages tracking the slightly reduced wave speeds in the southeast corner of the Yilgarn. Again, my inference would be that we've seen modification of this with the guiding hand of the older stuff. And again, we've got Huayu's model that show similar structures. All right, now in terms of mineralization, so everyone will have seen this map at this stage. So this was Mark Hoggard's work. We've got sediment-hosted mineral deposits superimposed and a map of LAB thickness that was derived from a seismic tomography model. And then the contention that 85% of these base metal deposits occur within 200 kilometers of this transition between thick and thin lithosphere. As Ruth pointed out, we we don't have, especially at the time of generation of this model, so this was back in 2012, we didn't actually have that many stations in WA. So it behoves us to refine that LAB model. Now, like I said, Graham has been a long-time proponent of this, but more recently we've seen a slew of papers emerging pointing to this, the role of lithospheric thickness in modulating the generation of mineral systems for the different types of mineral systems. So this one at the bottom was published just a couple of weeks back, talking about carbonatites. But yeah, we have different tomography models. We'll give you slight variations on the LAB map. So this was from OSRAM. This was published around the same time, 2013. And then we have another, this is extracted from a global model around the same time again. So what can we say about this? Just to sum up, this will be the last slide. So we have an older West Yulgaren seismic thicker. On the right-hand side, it's the derivative LAB map with the locations of deposits superimposed. So last year we pointed out the coincidence of the Southern Cross domain gold deposits with this this kind of step and lithospheric thickness. I would say as well, now we're getting into, I guess, second order boundaries. So looking at these big global models of lithospheric thickness, but we're now looking within cratons themselves, and more complexity is added by the fact that, say, the Southern Cross komatiites there are up to 2.9, but the mineralization was 200, 300 million years later. So we've got to take that into account as well. The other thing I would point out, so that area of very fast wave speeds, so it's up to 4.8-ish. If I look at it in the corresponding, it's hatched in with the blue dotted line in the LAB map. So not many mineral deposits within that zone. So if we go to South Africa, we have these examples of these xenoliths that are erupted. So at the margins of these very high shear wave velocity zones. So I would say we're seeing something similar here. I think this may be the nut that was too tough to crack. So this old, robust, rigid protocraton keel, and that just couldn't be penetrated by, or not as much as the rest of the craton anyway. Yeah, we've made a start on trying to interpret this stuff. Yeah, more to come. I'll stop there.